In this presentation, we're going to be looking at how we can apply Hess's law to using enthalpies of formation for finding the enthalpy change for a reaction that it would be impossible to measure. In this particular reaction, the impossible reaction that we're going to look at is the enthalpy of decomposition of calcium carbonate. So calcium carbonate or chalk is what the White Cliffs of Dover are made of, and unless you heat these to a very, very high temperature, they'll stay as the White Cliffs of Dover. That's calcium carbonate and chalk. And if we heated it to a very high temperature, eventually they decompose to calcium oxide and carbon dioxide. But there's no way we can measure the heat energy needed to do this, because it really it would be really high temperatures and not all of it may decompose. So what we have to do is to go by another route. So as I mentioned before, the reaction is really endothermic. We need to put a heck of a lot of heat energy into that reaction because it's a decomposition reaction to make that decompose into its two elements. So instead, what we're going to do is to use standard enthalpy of formation to find the enthalpy change for this enthalpy of reaction here. Just a quick recap. There's the definition. The standard enthalpy of formation is the enthalpy change, and again, it's always the start. The standard enthalpy of something is the enthalpy change when 1 mole of a compound is formed from its constituent elements in their standard states, which is at standard temperature 298 Kelvin and 100 kilopascals. So what are the elements, the constituent elements of both the reactants and the products? So here's the reactants and here's the products. Well, both are made up of identical elements. Otherwise, the elements in the reactant side can't differ than the product side, otherwise you've created matter. So the elements that are present in the reactants are calcium. So here they are down at the bottom. These are the elements. And you have carbon. And you also have 1.5 moles of oxygen gas, which is equivalent to 3 atoms of oxygen. Notice that the elements that are present in the reactants are also present in the products. There's your calcium atom, and there's 1, 2, 3 atoms of oxygen and an atom of carbon. So what we can now do is, let's first of all look at the enthalpy change of the formation of calcium carbonate. So here are the elements. So this enthalpy change here, delta H1, is the enthalpy of formation of calcium carbonate. So there it is, the enthalpy of formation of calcium carbonate. If we now look at the other enthalpy change, this is the enthalpy change 2. These are the products. So this one here is the sum of the enthalpy of formation of calcium oxide and carbon dioxide. So this symbol here, the sum of adding those two together. So this is the enthalpy, the sum of the enthalpy of formation of the products. Whereas delta H1 is the enthalpy of the sum of the enthalpy of formation of the reactants. However, there's only one reactant, so we don't really need to sum it. But in other examples, you might find that there are more than one reactant. So let's now move on to look at how we can use Hess's law. So here, the data that we've been given, so it's important to look at the data you've been given. So this data is enthalpy of formation of the calcium carbonate, which is the reactant, and also the enthalpy of formation of the product. So we've got the enthalpy of formation of calcium oxide here, but we also now need the data for the enthalpy formation of carbon dioxide. Now, just to remind you, the chemical equation for enthalpies of formation, forming 1 mole of a compound from its elements, in their standard states. And the chemical equation for the enthalpy of formation of calcium oxide is 1 mole of calcium oxide in its solid state from its elements in their standard states. So here's the third piece, the missing piece of data we need, the enthalpy of formation of carbon dioxide. So what we're going to do with this enthalpy of formation data is we're now going to apply it to this cycle here. And if we look at this cycle here, I'm now going to give it my cheeky little names from the Great Escape. So this tunnel is called Tom, and this tunnel is called Dick, and this tunnel is called Harry. And we put little kinks in these tunnels, and you can see that Tom and Dick are happily going off in a clockwise direction, and Harry is going in a clockwise direction. So if we now apply Hess's law, which states that the enthalpy change is independent of the route taken, we can see that Tom and Dick are going in the same direction. So I'll just write here, according to Hess's law, that Tom and Dick are going in the same direction, and Harry is going off in, as you can see, in an anti-clockwise direction. So here we're trying to measure this unknown enthalpy change, which we can't measure in a million years, which just happens to be Dick. So we put him on his own. So we need to take away Tom from him. So we take away Tom from Harry as well. So what we can now do is we can now put our values into this equation, and we can also, instead of using an energy cycle, we could write a general equation if we are given enthalpy of formation data. So our little equation, if we're given enthalpy of formation data, the enthalpy change for the reaction, for any reaction that you can't measure, if you're given enthalpy of formation data, here you can see that Dick, this one here, is the enthalpy of reaction. Harry just happens to be the enthalpy, the sum of the enthalpy of formation, the enthalpy change of formation, this time of the products. And Tom just happens to be the sum of the enthalpy of formation for the reactants. So what we can now do is to substitute this into this equation here. Harry is the sum of the enthalpy of formation of the products. And Tom is the sum of the enthalpy of formation of the reactants. So now we can put our values into this equation, and we will then come up with an answer for the enthalpy of decomposition of the calcium carbonate. So underneath it, I'm going to write the enthalpy of reaction that we're trying to find, the enthalpy change for the reaction that we're trying to find. So the sum of the enthalpy of formation of the products is, I'm going to put it into brackets, it's the enthalpy of formation of, and I'm going to write it in, calcium oxide added to the enthalpy of formation of carbon dioxide, close brackets, take away the enthalpy of formation of the reactant, which is calcium carbonate. Now I'm going to put my values in. So I'm going to write this underneath to show sequentially. So the value for calcium oxide is minus 635 kilojoules per mole, added to a minus carbon dioxide, which is a minus 394 kilojoules per mole. And from that we take away the enthalpy of formation of calcium carbonate, which is minus 1207 kilojoules per mole. So the enthalpy of reaction is equal to the sum of these two, which is minus 1029. Notice how I'm writing it out sequentially, each step below the other. Don't just write random numbers all over your exam paper. So that's minus a minus, which becomes plus 1207. So the enthalpy change for the reaction in this case is endothermic as we predicted, and it's plus 178 kilojoules per mole. 3 significant figures, because that's the maximum number of significant figures we've been given in the question. So here's a little way of trying to remember, rather than trying to remember the equation, so you could get it back to front. If you're given enthalpy of formation data in your exam question, and we'll go through one in a moment, then the enthalpy cycle, here are your elements, so I often draw a little elephant, because it sounds like elements. There's my little elephant with his long ears. And my little elephant is in a hot air balloon going up to heaven. So imagine your element or your elephant being taken up into the sky. So what we're now going to do is to look at some exam paper questions where you're asked to calculate the enthalpy change for a reaction when you're given enthalpy formation data. In this question, the first part asks you for the definition of standard enthalpy formation. So it's really worthwhile, those gimme marks is to learn your definition. I'm going to call that a gimme mark. So 3 marks for a definition, come on. So the next question here gives us enthalpy of formation data. Now notice the F, because this is a pre-2016, is written after the H. But this is enthalpy of formation data. Here is the enthalpy change for this reaction we're trying to find. So what I'm going to do is 2 ways. I'm going to do it first, we're using an energy cycle, and then using an equation. So if we look at the reactants, that's your magnesium oxide, and your products are your magnesium chloride. So I'm going to draw an enthalpy cycle. So it's magnesium oxide, it's reacting with your hydrochloric acid, and we're forming magnesium chloride and water. So don't forget that these are your reactants and these are your products. So the elements that these are made up from are magnesium, and we know magnesium is a metal, so I'm going to give it its symbol, because remember these have got to be in the standard states. I've not bothered writing the standard states, the states of the products and reactants, but this is really important just in case. So there's magnesium, there's oxygen, which goes around as a gas, so that's a half O2. Why? Because there is 1 mole of oxygen here, and half O2 gives us 1 mole of oxygen atoms. Also to note, there's hydrogen, and hydrogen goes around as a gas, and that's 1 mole of H2 gas. And we've also got the element chlorine in here. We've got 2 moles of chlorine atoms, which is 1 mole of chlorine molecules. So don't forget that chlorine and hydrogen and oxygen are all diatomic molecules in their standard states. So these are our elephants or elements at the bottom here. And the elements that react to form the reactants are exactly the same elements that react to form the products. And therefore here is the sum of the enthalpy of formation of the reactants. And here, this is the sum of the enthalpy of formation of the products. So using Hess's law, I can say that the enthalpy change for reaction that we're trying to find, delta HR, I'll put the R there, for the reaction that we're trying to find, is the sum of the enthalpy change of formation, looking at this cycle here. So there's Tom and Dick, and there's Harry. So using Hess's law, the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants. So either you can use the enthalpy cycle or you can use the equation. but it's best to learn from first principle the enthalpy cycle. So now let's put our data in. Well, the products is magnesium oxide, so I'm going to write minus 602 there. And we've also got water, which is minus 286. And magnesium oxide is minus 602. And 8 hydrogen chloride is minus 92. But we are reacting 2 moles of HCl, so we need to times that by 2. And we're forming 1 mole of water, so that's fine. So don't forget that this value here, the enthalpy of formation of hydrogen chloride, has to be times by 2. So now underneath, again, make your enthalpy of change for the reaction. Make it sequential using a logical order and keeping your calculation nice and tidy. So the enthalpy of formation of the products is your magnesium oxide. So that is minus 602. Added to the enthalpy of formation of water, which is minus 286. Take away the enthalpy of formation, or the sum of the enthalpy of formation of your reactants. And the enthalpy of formation of your reactants is 1 mole of magnesium oxide, and that's minus 602, added to the enthalpy of formation of 2 moles. Don't forget your 2, because you're forming it's the enthalpy of formation of 2 moles of hydrogen chloride, which is 2 times minus 92. Now you can dive for your calculator, but I'm going to work out them separately rather than put the whole lot in my calculator, because there's always a chance I can hit the wrong button. I just realised I did a deliberate error that I pointed out to myself, and this is really easy to do under exam stress. Notice I put the enthalpy of formation for magnesium chloride at minus 602 when it's actually minus 642. So that is minus 642, and therefore we need to change that. So that becomes minus 926. So this is a reason why in an exam always write out stepwise, because you would still get almost full marks. So now put those two into your calculator, and the answer is minus 142 kilojoules per mole. So always show your answer in broken up steps. Make sure you have either the cycle and or the equation for the reaction, and make sure you don't be tempted to put all of your numbers directly into your calculator, because even if you mistranscribe a number, the marker will see that you followed the correct steps.